Okay, it is January 19th, 2026. And if you've been following the news in astrophysics for the last, few years,
Yeah.
you know it has been volatile.
Oh, yeah. A total roller coaster.
We've had these headlines just screaming that the Big Bang is a bust or that our whole understanding of physics is just, broken.
Well, that's what happens. You turn on a revolutionary new machine like the James Webb Space Telescope, and it breaks things before it can start fixing them.
But today, looking at this stack of sources, we've got some heavyweight studies from late 2025, a few papers from, effectively this week. It feels like the dust is finally settling.
It does. We're seeing a new story emerge.
A story where the standard model of cosmology isn't crumbling, it's actually flexing its muscles.
It's a story of resilience, really. It turns out all those crises we were panicking about might have just been growing pains.
We have a lot to get through today. We're going to look at a brand new proposal that might, it might delete the need for that God particle at the start of the universe.
From Raul Jimenez and his team, yeah. And then there are the little red dots.
The universe breakers. We're digging into Dale Kuczewski's findings that finally explain what those were.
And the big one. We might finally have a resolution to the Hubble tension.
The biggest fight in cosmology, thanks to Wendy Friedman's team.
It's a big deal.
And after all that, we'll take a quick trip to the labs hunting for dark matter, and then end up right in our own stellar neighborhood to see if we've actually found life on TRAPPIST-1m.
Sounds good.
So let's start at the beginning, the very beginning. I'm talking 10 to the power of negative 36 seconds after the Big Bang.
The inflationary epoch.
Exactly. So for everyone listening, the standard story is that the universe didn't just, expand gradually. In that first tiny fraction of a second, it ballooned exponentially.
All right, and that's what smoothed everything out. It explains why the cosmos is so flat and uniform today.
That's the inflationary paradigm. It works, it fits the data we see, but theoretical physicists have always kind of hated one part of it.
The inflaton.
The inflation field.
Yeah. To make the math work, we had to invent this hypothetical field and a particle to go with it that drove the whole expansion. And worse, we had to fine-tune it.
This is the adjustable knobs problem, isn't it?
Exactly. It's like having a radio that only works if you turn 5 different dials to this one microscopic exact position. If your theory needs that much fine-tuning to match reality, is it really a fundamental law?
Or are you just forcing it to fit? It feels engineered.
It does. And so enter this new study from July 2025 from Raul Jimenez's group. They're basically saying, let's throw away the knobs, let's throw away the inflaton.
Which is a pretty bold move. Physics usually gets more complicated, not less.
It is bold.
So what do they replace this magic particle with?
Gravity, just gravity itself. Specifically gravitational waves in what it called a de Sitter space.
Okay, we should probably define that. De Sitter space sounds like something out of science fiction.
It does, but it's a specific mathematical idea. You imagine a vacuum that isn't really empty, it's dominated by its own internal energy.
Sort of like what dark energy is doing to our universe right now.
Precisely. And what Jimenez's team argues is that if you start with that kind of state, you don't need some external field to kick things off.
You just need the ripples in space-time itself.
The quantum oscillations, the gravitational waves. And here's the real breakthrough. They showed that these waves interact with each other non-linearly.
Non-linearly. So they don't just pass through each other like ripples on a pond.
They crash. They build on each other, they interfere, they create complexity out of a very simple starting point. The paper shows that these gravity waves, just by interacting with themselves, could create the little density differences.
The little clumps.
The clumps that eventually became the seeds for every galaxy and star we see today.
So instead of needing some special particle to say, okay, matter goes here, it's just the fabric of space-time sort of crumpling up on itself.
It's Occam's razor in action. It explains the whole structure of the universe using only general relativity and quantum mechanics. No new particles needed.
And the best part is, this is a testable idea.
That is the key. The old inflaton model was slippery. You could always just retune the knobs if new data came in. This gravity-only model makes hard predictions about the shape of the cosmos. Predictions we can actually go out and measure.
So future telescope surveys will either prove it right or
kill it. And that's what good science needs. Theories you can actually kill.
Okay, so we've rewritten the first second of time. Let's jump forward now. Let's go to the cosmic dawn. About 600 million years after the Big Bang.
Ah, the era of the little red dots.
I just love that name. The astronomy community comes up with this unassuming name for something that was threatening to completely break the standard model.
And they really were a threat. When JWST first started sending back data, it saw these compact red objects everywhere in the deep past, and they were bright, unbelievably bright.
And in astronomy, brightness usually means mass, right? Lots of light, lots of stars.
That's the normal conversion, yeah. And when they ran those numbers, the little red dots implied galaxies that were just impossibly massive.
Like Milky Way-sized galaxies forming when the universe was just a toddler.
Exactly, and that's the universe breaker problem. You just can't assemble that much matter that quickly with the known laws of gravity. There just wasn't enough time.
Which led to all those panicked articles. Is the Big Bang wrong?
Do we need new physics? Yeah, all of that.
But now, this month, January 2026, Dale Kolschewski from Colby College and the Sears team, they presented their solution. And it turns out we were just looking at the wrong kind of light.
Or maybe misinterpreting the source of the light. The team did something really smart. They didn't just count the photons, they dissected them. They looked at the whole spectrum of energy.
And they found these dots had a kind of split personality.
They did. At long infrared wavelengths, they look red and angry, which you'd expect from a lot of dust. But at shorter wavelength, visible and UV light, they saw a distinct blue component.
And blue means young stars.
Right. But the red part, it wasn't just old stars, it was intense concentrated heat. And the real clincher was the velocity measurements.
This is the part that just blew my mind. They measured how fast the gas was moving inside one of these tiny little dots.
Using the Doppler shift, yeah. They found gas swirling at 1,000 kilometers per second.
Which is what, like 2.2 million miles an hour?
Something like that. It's insane, and you do not get stars orbiting that fast in a normal baby galaxy.
No, that kind of speed only happens
in the grip of a monster. It's the unmistakable signature of an accretion disk feeding a supermassive black hole.
So these little red dots, they're not impossible galaxies, they're baby quasars.
They're active galactic nuclei. The incredible brightness wasn't coming from a trillion stars, it was coming from a relatively small black hole just eating gas as fast as it could.
And because black holes are so efficient at turning matter into energy,
a small object can completely outshine an entire galaxy full of stars. So once you subtract that glare from the black hole, what's left of the galaxy itself?
a completely normal, small, infant galaxy.
Perfectly in line with the standard model. No crisis.
It's almost funny. We were so sure the universe was broken, but really, it was just a case of glare. Like we were blinded by headlights and thought it was a giant truck, but it's just a motorcycle with a really bright beam.
It's a perfect analogy. And they see these things peak around 600 million years and then fade by about 1.5 billion. It was a phase, a growth spurt for black holes.
So another crisis averted. Which brings us to the next big one on our list. The one that's been keeping astronomers up at night for a decade. The Hubble tension.
Oh, this one. This was much harder to explain away than the red dots. This wasn't just a misreading of a single image. This was a deep, systematic disagreement between our two best methods of measuring the universe.
Okay, so on one side, you have the early universe team. They look at the cosmic microwave background.
Right, the baby picture of the universe. If you take that picture and you use our current physics models to roll it forward to today, you get a very specific prediction for how fast the universe should be expanding.
Which is 67.4 kilometers per second per megaparsec.
67.4, that's the prediction. But then you actually look out the window at the local universe.
And you measure it directly using standard candles, like certain types of stars. And for years, the Hubble Space Telescope gave us a number that was more like 73 or 74.
And 67 is definitely not 73. The error bars didn't even overlap. And that was the tension. It meant something was wrong with our model.
Maybe dark energy changed over time, or maybe we needed some kind of new physics.
And this is where Wendy Friedman comes in. I mean, she is absolute royalty in this field. Her team basically nailed down the Hubble constant in the 90s, and now she's going back to check her own work.
But this time with JWST. What's the advantage? I mean, the Hubble telescope was literally built for this. It's in the name.
It was, but Hubble had its limits. The main way we measure these distances is with Cepheid variable stars. They pulse. But the problem is, Cepheids tend to live in the disks of galaxies.
Which are crowded places.
Very crowded and dusty. So for Hubble, what looked like one Cepheid star might have actually been that star blended with light from 2 or 3 other stars in the background that it just couldn't separate.
Which makes the star look brighter, which makes you think it's closer than it really is.
And if your distance is wrong, your whole calculation for the expansion speed is wrong. JWST has much sharper vision. It can pick that single Cepheid out from the crowd, But Friedman's team went a step further.
They didn't just rely on the Cepheids.
No, they used two other types of stars. The tip of the red giant branch and these things called J-region carbon stars.
Are they just more reliable?
They're cleaner targets. Red giants are found in the halos of galaxies out in the suburbs, away from all the downtown dust and crowding. So by using all three methods, with JWST's incredible resolution, they could finally strip away all those old systematic errors.
And when the dust literally settled, what was the final number?
70.4 kilometers per second per megaparsec,
70.4.
with an error margin of about plus or minus 3%.
And the early universe prediction was 67.4.
Which means they overlap. Statistically, there is no significant difference anymore. The tension is gone.
You know, I feel like this must be a bittersweet moment for some theorists. New physics is exciting.
It is.
Finding out it was just measurement error is, well, it's good science, but it's not as sexy.
It's not as sexy, no, but it's incredibly reassuring. It means our understanding of the universe from the Big Bang right up to today is actually consistent. We don't need to break physics, we just needed better classes.
So gravity can explain the very beginning. Black holes explain the impossible galaxies. And better data resolves the expansion crisis. The standard model is having a really good day.
It is. But let's not get too comfortable, because while the model holds up, we still have no idea what most of the ingredients are. We still don't know what dark matter is.
Which is, what, 27% of the entire universe?
Roughly, yeah. And we've been hunting for it for decades. But our sources mention a new experiment from Rupak Mahapatra's team at Texas A&M, the Tesseract project.
Tesseract. I love it. Sounds like a Marvel movie. But they're looking for WIMPs, right? Weakly interacting massive particles.
The classic candidate, yes. The trouble with WIMPs is that they're basically ghosts. Billions of them are passing through you right now, and they don't touch anything.
So how on earth do you catch a ghost?
You build an extremely quiet room, and you wait. You wait for that 1 in a trillion chance that a WIMP accidentally bumps into the nucleus of a regular atom.
And that bump would be tiny.
Infinitesimal. It would create a single vibration, a phonon. And this is where the new tech comes in. At normal temperatures, atoms are vibrating like crazy just from heat. You'd never hear the wind.
You have to freeze everything.
Right down to near absolute zero. Tesseract is developing these new cryogenic quantum sensors that can detect a single phonon of vibration in a supercooled crystal.
The analogy they used was trying to hear a whisper in a hurricane.
And cooling the detector is how you stop the hurricane. If you can get the environment perfectly still, that tiny whisper becomes audible. It's high risk, high reward. If they get a ping, it changes everything.
And if they don't?
Then we might have to rethink dark matter from the ground up.
Okay, high stakes in the deep freeze. Last stop on our tour. Let's come back home, or at least to the neighborhood. 39 light years away. The TRAPPIST-1 system.
Ah, everyone's favorite, the 7 Earth-sized planets.
And all the attention is on TRAPPIST-1. It's in the habitable zone, the Goldilocks zone. And recently there was a lot of buzz that JWST detected methane in its atmosphere.
And methane is a huge biosignature. On Earth, most of it comes from life, but, and this is a really big but.
Here it comes, the reality check.
The reality check, yeah. It comes from Sucrit Ranjan at the University of Arizona, and he's warning everyone about star noise.
Explain that. How can the star itself fake a methane signal on a planet?
TRAPPIST-1 is a red dwarf. It's much cooler than our sun, but it's also way more active, with magnetic spots and flares. Ranjan's work suggests that the spectral dip we're seeing, the thing that looks like methane, might actually be caused by elements on the surface of the star itself.
So when we're looking at the planet, the star is photobombing the picture.
That's a great way to put it. We're looking at starlight filtering through the planet's atmosphere, but if the starlight is already dirty with a signal that mimics methane, we get a false positive.
That is so frustrating. So is there a way to filter that out?
There is, and it's brilliant. It's called the dual transit technique.
This involves using one of the other planets, TRAPPIST-1b.
Exactly. TRAPPIST-1b is the innermost planet. It's a scorched, airless rock. It's completely dead.
So it's our control group.
It's the perfect control group. You watch Planet B, the dead one, pass in front of the star. If you still see that methane signal...
You know it's a lie. It's coming from the star.
But if you see the signal on Planet E, the habitable one, and not on Planet B...
Then you've got a real detection.
Then you might have something. And the upcoming Pandora mission is designed to do exactly this. To stare at these stars and map out their noise so we can subtract it perfectly.
It all comes back to having better tools and cleaning up the data, doesn't it?
That really is the theme of this whole deep dive today.
It is. We started out with a universe that looked broken on all fronts. The Big Bang seemed wrong, the first galaxies looked impossible, the expansion rate didn't make sense.
And even the potential alien signals were confusing. But when you apply that next level of rigor, when you remove the knobs from your theory, or use red giants instead of Cepheids, or use a control planet, the anomalies start to vanish.
And what's left standing is the standard model. It's surprisingly robust.
It's a good reminder that extraordinary claims, like physics is broken, they require truly extraordinary evidence. And right now, the evidence is actually pointing back toward a more orderly picture.
I want to leave you with a final thought on that. We talked about the little red dots being these black holes that formed super early, and the new inflation theory where gravity just sets everything up almost instantly.
Right.
If that's all true, it suggests the early universe wasn't this messy, chaotic explosion. It was hyper-efficient. It built the seeds of all cosmic structure in a fraction of a second. It grew supermassive black holes in just a few 100 million years.
That's a fascinating way to look at it. We always think of chaos and entropy, but maybe the fundamental machinery of the cosmos is far more precise than we ever gave it credit for.
Or maybe we're just finally getting smart enough to read the blueprint.
I like that. We're finally reading the manual.
We are, and there are a lot more pages left to turn. Thank you for joining us on this trip through the universe.
It's always a pleasure.
And to you listening, keep looking up. The universe is making more sense every day, but it definitely hasn't run out of surprises for us yet. We'll see you on the next deep dive.